Over to Shakir.
Okay. So, welcome back, everyone. Hope you had a good lunch. So, let's just finish this second bit. So, I'll just remind you I wanted to have two learning objectives for this session for you to develop and manipulate 6 tools for manipulating probability questions, and then to think about how they connect to different fields. And we looked at all these inferential questions, evidence, prediction, planning, hypothesis testing, and we looked at one trick, which was this trick, the identity trick, how you change an expectation from one distribution to another by multiplying by a 1. And then we spoke a lot about importance sampling, conditions under which importance sampling works, why you want to do importance sampling, and this important question, the role of estimators when computing integrals. So we're going to do the next set, 5 more, and so please ask lots of questions, and we can take it a bit easy while we come back from lunch. So this one here is called Hutchinson's trick, and obviously, there are many sort of problems that you will find when you're dealing with matrices and distributions. And one of those things, the core question of numerical algebra, is to compute the trace of a matrix. Now, this seems like a very simple thing, just sum up all the diagonal entries. Why is there a trick needed to compute the trace? But typically the trace is going to be a thing of linear algebra that's going to compare in a lot of places. If you look at the KL divergence between two Gaussian distributions, then what you're going to ask there is to compute the trace of a product of two matrices. Or if you want to look at the gradient of a log determinant, this is a problem you will find in lots of problems. Linear regression has it, Gaussian process regression has it, any other ways of looking at combinatorial maths will have this kind of problem. Then you're going to face this difficult problem of how do you actually compute the trace. So again, for example, if I have the log determinant of a matrix X and I want to compute its gradient by matrix algebra, I'll know that the gradient is the trace of X inverse times the gradient of X. So now I need to compute the trace of a product of two matrices, and the naive thing to do is to invert the matrix X, compute the gradient, multiply the two, then sum up the diagonal. But you're actually only interested in the diagonal in the end, so this is the thing that we're going to exploit, that maybe there are ways we can be more efficient about computing the trace rather than just doing this inverse, which is going to be a cubic computation in the dimension of the matrix X. So if the matrix is n dimensions, then there's going to be an n cubed computation, and so we're going to think about this. So here's our problem, as we always do. I'll derive them with these little green boxes. I'm going to compute the trace of a matrix A. Now, this is a very useful, in itself maybe a trick, that the expectation of two zero variance properties or two zero variance vectors is the identity matrix. So it's a variation of the identity trick before, right? So Z is a 0, 1 Gaussian, for example, a vector. The expectation of ZZ transpose in general is sigma, the covariance of Z times MM transpose, but because Z is a zero mean vector, M is 0 and MM transpose is 0. So all of this then is just that, but then the thing is it was a unit variance Gaussian, for example, so the mean, the covariance of a zero variance Gaussian is just the identity, so that's why this thing is I. So I'm just going to use this identity trick to multiply the trace by 1. So the identity trick in this kind of particular form is to take the trace of A times the identity. Now, and I'll replace the identity with this up to this objective, this expectation, times the expectation of Z times Z transpose. Okay? Hopefully, let's just look at it a little bit more so that we all follow. Now, there is a useful property of the trace. The reason why the trace is loved so much is that cyclic property of the trace, that you can rotate things within the trace and the number will still be the same. So we're going to use that linearity of operations, 2 of them. One, that the expectation, because it's an integral, is a linear operator. So I'm going to take the expectation out of the trace. The quantity is still going to be the same. And now I'm going to use this idea that I can rotate things circularly within the trace to reorder this term. Right, so I can say that this is going to be equal to the trace property lets me take this Z transpose and put it on the other side, and that quantity is still the same, right? So hopefully everyone is following up to this point. So now I have the expectation of Z transpose times A times Z. Now already this is a very useful form because all I have is products of matrices times vectors, and matrix times vector products are efficient ways of doing computation. They are always quadratic computations, whatever the size of the matrix A is. So this is basically the trick. I'm going to sample Z's randomly from some zero mean unit variance distribution. I'm going to compute this expectation by creating a Monte Carlo estimator, and the number that I get in the end is going to be the trace that I'm interested in. So does sort of everyone follow roughly what's going on? So let's follow that. I have a vector Z. One distribution to sample from is called the Rademacher distribution. The Rademacher distribution is just a distribution on zeros and ones with probability half. So it's a Bernoulli where you set the probability to half. So I sample, let's say I have n-dimensional matrix A, it's n by n. I sample a vector of zeros and ones from the Rademacher distribution, will be an n-dimensional vector. I compute this quantity Z transpose A times Z, and I can compute it a few times to average that. And that number that I get in the end will be the trace of that vector. So now, on its own, it may just seem like a very simple kind of trick, and I haven't really done that much. But when you combine it into problems like this one above, then we'll be able to remanipulate the terms to turn everything, instead of matrix products, which is what we might have up there in the log determinant question, into systems of linear equation solvers, which will be x inverse times z. That requires a system of linear equations to solve, and solving systems of linear equations can be done quadratically or a bit more efficiently than inverting and doing it naively. It will also be more numerically stable. So this is a method that both helps us with computation, but also with numerical stability. So that was just a cute little trick that I wanted to throw at you that shows the use of the identity trick in a different way. Does anyone have a quick question, maybe a thought, or just wants to go through this derivation one more time before we go on to another trick? Yes? Oh yeah, I'm using this weird notation partial x just to say the gradient of x with respect to whatever parameters I might be interested in. So here, let's say x has a set of parameters inside. So maybe let's say one entry of the matrix itself is the parameter. Then I will compute the gradient, let's say, with respect to theta I of this object. So I'm just writing this as a shorthand for there's a gradient that you are actually interested in, and it's a function of x. Any another sort of question? Yes? So the question is, it's still quadratic cost. Are there ways of saving computation even further in some way? There's maybe a few answers to that question. So one question around computation is, how many samples do you actually need to compute the average itself? And actually, there's a little bit of a proof you can all do. It won't take long, maybe 5 lines, just for each to compute actually how many samples you need under two distant distributions for Z. Should you use this 0, 1 binary vector for Z, or can you use instead a Gaussian, for example? And which one is more efficient and which one is not? And through that kind of proof, you'll be able to show that the Gaussian is slightly better. There's a sort of, again, a variance and sample size trade-off. To get to the point of doing linear equations or a linear cost, I don't know if you can do that. The trace is fundamentally this operation that operates in a matrix. So you may be able to shave off a few other things, but I'm not sure. But in general, maybe the point, this is maybe an entry point for all of you in what they call stochastic numerical methods, or probabilistic numerical methods, or probabilistic linear algebra. And there's a whole area of research around probabilistic methods or ways of approximating numerical quantities and numerical algorithms through stochastic approximations like this that exploit the fact that expectations of zero mean quantities are this way, or approximate computation through other kinds of probabilistic methods. Very big area of research, so it's a fun one to look into. Any other thoughts on the on Hutchinson's trick? So Hutchinson's version of the trick uses this 0-1 Gaussian, and then of course later on other people use Gaussians and other kinds of things. So it doesn't really have another name. Okay, so let's go on to this another trick. I call this one the probability flow trick. So the question here is, I want to work not just with simple Gaussian distributions, but I want to work with very complicated distributions. So is there a way I can start with simple distributions that I know, but use those simple distributions to create complicated distributions while still making them easy to compute, meaning that I can use them in my models in simple and efficient ways. So aspects of computation, simplicity, and complexity, I sort of want all of these three things in one, and this is maybe one trick to help achieve that. So let's start with a simple observation that if I have a probability distribution on X, I can generate samples from that probability distribution. So I'm just going to assume that case. So I'm going to call the samples from the probability distribution X hat. Now I'm going to transform those samples through some kind of function. We'll call that function G. G may itself have parameters theta that I can tune and twist. So I'm going to transform x hat using some function g, and the output of x hat I'm going to call y hat. So this is the setup. And now there's this law, it's called the law of the unconscious statistician. And the law of the unconscious statistician is that you don't need to be mindful. If you wanted to know the probability distribution, sampling y, if you wanted to get the x samples from the expectation of g, you can just do this system and just average over y. So you don't need to know the distribution of y. You only need to know the initial distribution x that you started with, and then you can sampling x, push it through this function and compute the average, and that will be the correct answer. So it's nothing more than you think. It's doing exactly what I described. So, but you can do one other thing, which is, what is the distribution y if I change this distribution p of x using this function g? And so this is this famous identity, which is the change of variables for probability. It says, if I have a distribution x and I want to change it into a distribution y, using a function g, I can use this basic identity to know what the probability distribution on y is. What I need to do is take x, the original probability distribution, take the gradient of x of the transformation, which was g, with respect to the input variables. That gradient and the determinant and its inverse will tell me exactly by what proportion I need to reshape the probability distribution so that it matches a new distribution on y. So this is sort of a basic identity that you can always use. There is one assumption that's hidden in here, is that g must be an invertible function. So the invertibility is sort of something you can think about. Monotonic functions will all work in this case. If your function is not invertible, doesn't mean the rule doesn't apply. This version of the rule doesn't apply. If you needed to have non-invertible or sort of other weird functions that may have discontinuities, then you can use a more measure theoretic approach where you will actually sum exactly in the regions where all the probability, and you will track the mass, how it's changing over time. It's very complicated to do, so no one will ever actually do it that way. So for now, we're always going to restrict to this case. So here's the picture that I'm thinking of. I have an initial distribution z, which is going through a sequence of functions, which are these square boxes. These square boxes are what I'm calling the g's here. So I have the notation mixed up. Sorry, what's g here is what I'm calling x, and what's z here is what I'm calling y. And there are many kinds of these functions g that you can write out, and here's one kind of a function. It's just a linear function. This function says take some parameters w against z, so this is a linear function, times h, which is some pointwise non-linearity like a sigmoid, an activation or a link function. I can rescale it by u, and this kind of adding z is particularly useful as a feature because it tells you that this function includes the identity within the class of functions. If this term is 0, then f of z equals z, so the identity is there. But if this term is not 0, then you can take the identity and add something else to it. So if some of you have been working in deep learning, then you'll recognize this idea of adding the identity plus something as the core idea of a ResNet. but we will also use it in this kind of idea, what we call the planar flow. So we can do several kinds of things now. One of the reasons to consider a useful kind of computation is look at the log determinant of dz df dz. And I think maybe, is this the homework for you? Well, let's just skip this because time is running short. But if I had to give you this function, which is this nonlinearity, one of the key elements of this idea is that the determinant will be easy to compute. You will have a determinant which will be linear. So determinants in general are quadratic, at least cubic computations. So I'm choosing the kind of function so that the determinant of the gradient of that function will be simple to compute, will be linear, will be order of n. And so you can always do this. If you have the determinant of identity plus AB, you'll get this kind of a determinant, which is just a linear quantity. And so the determinant of using this function, I'll leave that for you to do a homework. So you get linear time computation of the determinant, and its gradients are the key thing to do. And the reason we want linear time computation of the gradient is because we want to compute the entropies, and entropies we need to compute efficiently, and we'll also be doing gradient estimation through backpropagation, and we want to have that computation not ever exceed quadratic cost. And the simplest thing to do is to start with a diagonal Gaussian and then just add these kind of functions, as many as you like, and keep reiterating this change of variables rule. And if you start with that, so I guess maybe this is just a bit more clarity on that point of linear time, that if you can choose functions whose Jacobians are triangular Jacobians will then always give you a linear time gradient of the determinant. So you can always, that's the key sort of insight that's being exploited there. I'm going to use this in a different setting, and I don't know, maybe I've not explained this quantity. So let's take a few questions and just talk about applying the change of variables rule to probability distributions. Any thoughts that you have around sort of what's happening here? Should I go through any part of it again? Looking good? Any thoughts, mumbles, grumbles? Grunts, groans, cheers, hears. Yes? Okay, so the law of the unconscious statistician says simply that I want to compute the expectation of some distribution. I know that this distribution has a structure, that it involves itself another distribution and a function that I transform that distribution through. So it simply says that to compute the expectation of the new distribution, I don't need to know the new distribution. Instead, what I can do is sample from the original distribution, push it through the function, and that will give you the correct thing. It's actually a trivial statement because the truth of Monte Carlo estimation also tells you that is true. But sort of that's one of the ways of thinking about that. Any other thoughts around change of variables? And yes? The unconscious statistician here, I just wanted to make the connection that one way of seeing this change of variables is being used in the unconscious statistician, but we're now going to use it. This particular thing of unconscious statistician, I'm leaving with you for us to use a little bit later. For now, we're going to consider this idea of computing simple linear triangular Jacobian transformation functions that give us linear time determinants. But I just wanted to connect the two because they are the same. You can either use the change of variables to compute P of y and then compute the expectation of P of y, or you can use the unconscious statistician rule to first get x, use g, and then compute the integral. All right. Maybe one more thought from the other side of the room? Okay, let's push this idea a little bit further to show you how it's sort of used in some of our other more advanced work in variational inference. So we call this idea normalizing flows, and it's just an application of this idea of this change of variables, this trick of making a probability distribution flow through a sequence of observations. So I'm going to start at time point 0 with a simple distribution, which is a Gaussian distribution. And I'm going to apply a sequence of invertible transformations to that distribution, with the aim that at the end I'm going to get a complicated distribution like that. Again, here's the rule for change of variables. I start with an initial distribution Q of Z, because if I can compute the determinant, the inverse of the determinant of the transformation of the Jacobian, then I can know the distribution at this point, and subsequently here, and subsequently here. But I'm actually going to use the structure here to show something different. If I use a sequence of K transformations, and I wanted to get a sample of the distribution at time point K, I never need to compute the distribution. I just need to sample from the initial point and apply each of the composition of these functions at the end. And the variable that I get at the end will be a sample from the complicated distribution. I think that this is, again, that unconscious statistician and drawing samples from the complicated distribution. I just need to sample from the simple distribution, apply the sequence of functions, and the variable that I get at the end is a sample from the complicated distribution, and I do that without knowing the complicated distribution. I think that bit, I hope I'm stressing it enough. You never need to know the complicated distribution. The second bit is that I want to compute the entropy. Now, the entropy of a distribution is the expectation of the log probability of a distribution under itself. So this is it, and you can compute an estimate of the entropy just by evaluating the log probability of the distribution under one sample. So that's basically what we're doing here. If you want to compute log of Q of the entropy of the final distribution, you just need to compute one sample of that distribution at the end, and then you evaluate the initial distribution, which you know, it's just a Gaussian, with the initial sample, and then you just collect all the intermediate samples, compute this Jacobian, and sum up the log determinants. And the log determinant is simple to compute. This will be a linear operation, so it's just a linear operation to compute everything, and this number will be an estimate of the entropy of the distribution. So the reason to use the trick is that it makes sampling from the complicated distributions easy, and it makes computing an estimate of the entropy of complicated distributions easy. And if you know the entropy of a distribution and you can compute its sample, you basically know enough to do almost whatever you want to do out of it. I want to just show you visually what this looks like. So there are two rows here. The first row is a Gaussian, and the second row is a uniform distribution. And I'm showing you what happens when you apply many different transformations of a function. That linear function, which was the identity plus some linear term earlier. And what those transformations do, the reason it's a planar function, because it was using linear functions, they basically cut the plane of the distribution in half. So you take the Gaussian, you either squash it, you contort it, you tear it, you shear it, and that's basically what's happening here at every point. I squash it, I can split it in many ways, and this is what happens after applying 1, after 2, and after 10 different transformations. Similarly, I can do that with a uniform distribution, and you can see I can do planes, I can do multiple planes, and after adding many, many different kinds of transformations, you get very complicated distributions. You can imagine what happens as you go to 40, 4,000. So this is a very generic way of building very complicated distributions. I will just leave a note here for some of you who are a bit more advanced and have this knowledge of differential geometry, that you can use this kind of normalizing flow idea for non-Euclidean domains and non-Euclidean distributions. And the simple trick is to use the trick from differential geometry, where we form a chart, a mapping from the non-Euclidean space to an Euclidean space. We apply normalizing flows in the Euclidean space, and then we use the inverse of the chart, which is this mapping, back to the Riemannian or the non-Euclidean space. So you can do normalizing flows on spheres, on cylinders, on toruses, and these kind of things. And the generalization of this rule appears in differential geometry, and you'll see this little term, the determinant of J transpose J. The term looks a little bit different, but is exactly the same kind of principle underlying it. Okay, let's move on to another trick. Yes? Yeah. So the question was, can you put too many of these transformations? Do you learn some? Do you create a degenerative distribution somehow that's not useful for the problem you are dealing with? I do think in general, yes, there is a model selection problem applied to the number of flows that you have, one of the safeguards, for example, the linear flows, is that the identity function is included in the class. And the reason the identity function is there is exactly this point, is that because we are also learning parameters, parameters for very high levels of flows, hopefully they will be set to 0 or their contribution is very low, and then it's just the identity which is just adding. So it's a safeguard that in general we can allow ourselves to have more flows than we actually think are needed just in case. So that's the reason you can, and I think there is sort of a model selection question around how many of those flows that you have depending on the problem that you want, and it is a restriction of the capacity of the model. So yeah. Another question, yes, at the back. Just repeat that again. Is it possible? Is it? Okay, so this is an interesting question. The question was, how automated is this process of combining tricks? He was asking specifically at DeepMind and whether these kind of frameworks are open. Every trick that I described to you here is something that has now sort of become so basic that they are actually open sourced and they live in TensorFlow, for example, and many other in PyTorch as well, in Keras and other layers. I think the meta point that I'm putting about these tricks is that they are tricks that operate at many levels. Some of these tricks are tricks for theory and for you to manipulate probabilities, and in the end, the trick doesn't appear when you write the code because it has simplified other kinds of things. And other things, like the two tricks that are going to come afterwards, they are things which live in code, and those things are automated, or they are so simple that they are one line in the end of things. So I think maybe the third point is that the idea to explain these tricks to you is that I think we need many more tricks, and hopefully you'll be inspired to add to the book of tricks that we have to manipulate probability distributions. But ask me more about that afterwards. Yeah.
How would we use this for, let's say, our final distribution, we can take a few samples from it. So in this case, we knew what the parameters should be, so we knew what the transformations should be. But how do we learn what those parameters, what the transformation should be, given some output and some input distribution?
So the question is, how do you actually learn these transformations if you have inputs and outputs? Is that sort of the question? So the reason I'm asking you to have these two quantities to be available and that they should be easy, that the entropy should be simple and that it should be easy to sample, is that those are the two quantities you need to learn these kind of functions efficiently. So maybe you're asking two things and I'll try and answer both of them. One of them is that these functions f have parameters in them, and I need to differentiate those parameters to compute that, and so I'm going to show you how to compute that gradient in the next trick. But so one thing is, if you have this form, you can differentiate through the process of generating the distribution, which is why we need all these terms to be differentiable. All the f's are themselves deterministic and hence differentiable, and then we can compute these quantities. And usually the loss function will involve this log determinant term, and if you have that loss, then you can learn all the parameters, and that relates to the previous question around how many of these k functions that you need to have, and the learning process will involve maybe a hyperparameter sweep over the number of those k functions. But maybe you're asking in general, I don't know what class of functions, I don't know to use a linear flow or this kind of non-Riemannian geometric flow. What do I do there? And this is sort of a research question. And so today, many of the current research papers explore what are the kinds of flows that we can do. There are flows which are volume preserving, like the ones that I'm showing you, where always the volume of the probability is maintained, and others which are non-volume preserving. There are ones which are discrete time, like the ones that I'm showing. There are others which are continuous time. I'm showing you ones that have triangular Jacobians, and many of them, almost all of them, exploit this triangular Jacobian property, but there are a few that don't do that. So this is sort of a research question still. Any last thought on the normalizing flows? Okay, let's move to a new trick which will pick up on some of this and the questions of learning and gradients. So In general, there is a large area of probability theory, of machine learning, of operations research, of econometrics, of psychometrics, and optimization theory itself, which is called stochastic optimization. Many of you will know one half of stochastic optimization based on computing gradients through mini batches. This is a different part of stochastic optimization. And this is a gradient problem which is extremely fundamental. It says, I have an expectation of a function f of some variable z. The function may have parameters theta. I'm not going to be concerned with the parameters theta for this next two tricks. And I'm taking the expectation under the distribution Q, which has parameters phi. So I'm going to read the integral again. It's the integral of the distribution Q of z with parameters phi times the function f of function of z with parameters theta. And I want to compute the gradient of this integral, and the gradient is with respect to these parameters phi. Right? So I'm going to just say that again so that we all follow. I want to compute the gradient of an expectation of a function. The gradient is with respect to the parameters of the distribution. So this is the question, and this is the core question of this area of stochastic optimization. And in general, like we said before, you don't know the integral. The integral is intractable. It's very high dimensional. I won't know it in closed form. And it's specifically important that the gradient that I want is in the distribution Q. If the gradient was not in the distribution Q, I would just be doing maximum likelihood. I would just take the gradient of the function and then carry on. But because it's in the thing of the expectation, I'm going to have to manipulate this integral a little bit more because I won't be able to get a simple estimator to compute the gradient. The point is that I need to get an estimator. Again, as we said in the last few slides, an estimator is going to be something where it will be an expectation under a valid distribution times some function. And then I can do Monte Carlo and do that. So if I've lost you a little bit in this waxing lyrical about the structure of this integral, we'll see it as we unpack it a little bit. So you'll see this thing in many areas and under many different names. One of the largest areas that it's called is called sensitivity analysis. When you compute the gradient of an objective function with respect to any individual parameter, that is computing the sensitivity of that function with respect to the parameter. So sensitivity is a more general concept than computing a gradient because you don't need to compute sensitivities only by using gradients. You can use non-gradient methods to get the sensitivity. All of generative models and inference, many of the inferential methods that I spoke about, use this kind of exact question will come up. Reinforcement learning and control, the policy gradient theorem is exactly this question. If you are working in operations and research, I gave the example earlier about traffic light simulators and traffic light optimization. This is exactly the same question that appears there. If any of you are working in finance, what they call the Greeks, where you are computing risk of investment portfolios, you will compute exactly this integral against a pair function under some distribution of returns. And then if you're doing any asset pricing, it's always the same integral. The integral makes a lot of money, so we should be able to compute it well. And there are basically only two things. The integral has two things in it, so there are only two things we can typically do. Technically, there are a few more things, but we either can manipulate the function f, in which case I'm going to call that the pathwise estimator, and I'll explain this concept of a path a bit later, and then is either I will create a different kind of estimator, I'll call the score function estimator, where I'll manipulate the density Q. So only two things, and we're going to do two tricks, one for each of these manipulations. Right? So let's do the first one. These are what are called commonly in machine learning reparameterization tricks. I'm just going to get some water. So we just went through these probability flow tricks. And the flow tricks hopefully showed one important thing, is that distributions can be expressed in many different ways. I can start with simple distributions, and I can use sets of functions to create more complicated distributions, or I can know some kinds of complicated distributions themselves. So this is basically, I'm going to build on that trick to show you how to compute a gradient here. So I have a distribution Q of z, And this is now the complicated distribution, and I can sample from this distribution Q of Z. But almost every continuous distribution can be decomposed instead in a different form, where I instead sample from a simpler distribution, epsilon, and I get samples, and I also know a deterministic function which I will transform epsilon into samples of Z. Exactly the same idea of the normalizing flows in the flow trick. So where do you see this? The simplest one is the way you learnt about distributions maybe the first time. You learnt that you can sample from a uniform distribution, take the uniform, evaluate it through the inverse of the CDF function, and then you will get a sample from a probability distribution. This was the simplest way of doing what they call the inverse CDF sampling method for distributions. You did this for Gaussians, for other simple distributions. So that's basically what's going on here. Every distribution can be written in this form. And this function g is what I'm going to call a path. It is a path which will transform epsilons, or it is the flow, from epsilon using some other parameters phi into these sampled z. So again, this is very important. And we're going to manipulate the fact that if I see z as a distribution, I can rewrite it instead in this way. And I'm going to try and jump between the two. So this was the one that I gave you, was the inversion method for sampling. You can sample from the uniform distribution in 0 and 1, evaluate it through the CDF, and then you get a sample from the distribution at that point. The x that you get is a sample. So this is the most general, it's the default way, but typically you don't want to do that because computing the inverses of CDF are typically expensive. In fact, the inverse of many CDFs is not even implemented, or even its gradient is not implemented in certain places. So I always think of these flows as like a set of pipes. It is a pipe through which you put some kind of inputs, and through that pipes there's a mixing of different kinds of waters, other liquids, and out comes some new magical distributional liquid, which is the sample from a more complicated distribution. Again, that flow trick. So we're going to just try and follow the pipe backwards, and the flow of the pipe backwards will be the gradient that we need. So in general, these were called samplers. It's a way of sampling distributions, but they were also called one-liners. This is from a famous paper by DeVroy, where these distributions can be implemented in one line of code. So that's why they were called one-liners. And then the change of variables that we studied quite a bit already. So, okay, this pathwise estimator, and this is a non-rigorous derivation, and if any of you want to make it rigorous, you can actually follow that quite easily. So here's our integral problem. I'll read it again. It is the integral of a function f of z with respect to a distribution q, and I'm going to compute the gradient with respect to phi. And because it's the pathwise estimator, I'm going to focus my energy on the function f. I also know a transformation of this distribution q in terms of first sampling a simpler distribution epsilon and then getting this more complicated distribution using a known transform g. So I'm going to actually apply that. I'm going to say, well, q of z, because of the rule of change of variables, can be rewritten as p of epsilon times the Jacobian d epsilon dz. There's some terms which are lost out there. So that's what this first part of the integral is. Then I also said, everywhere where I see z as a variable, I'm just going to replace it by g of epsilon of phi, because that's the substitution, the reparameterization that I can make. So there was f of z, and I'm going to replace z by g epsilon of phi. And of course, I already have the p epsilon, so this is now all going to be integrated over epsilon. And then now I need to do dz, and just by using some differential calculus, dz is going to be g prime d epsilon, and so I can replace dz by g prime d epsilon. So now I've done the normal change of variables for integrals that we would do in calculus in first year, and then this is the new integral. Now I'm just going to try and cancel out the terms and simplify things. So one of the things you will find, so this is what I'm going to do. This term here, d epsilon dz, will itself, by using the inverse function theorem, will be 1 over g prime. So g prime and this quantity here are going to cancel, and they're going to disappear from the integral. This will work. This works exactly in univariate cases. If you are in the multivariate case, this is not going to work, but the result will be fine even in multivariate case. So G prime is cancelled, d epsilon dz is cancelled. So what we get is an integral of p epsilon times f as a function of g as a function of epsilon times d epsilon. So that's what I've written here. The gradient that I want is gradient with respect to phi of an expectation under a new distribution, which is a very simple distribution, p of epsilon times this reparameterized function f of g of phi. And because now the expectation is not dependent on the parameter, the gradient can just flow through the expectation, and then the real gradient is the expectation of p of epsilon times the gradient of f of g. And now the key point here is that f times g is the deterministic function. So this is just backprop, and it's a very simple gradient to do. You sample epsilon once, you compute this gradient, and the result that you have is the gradient. So okay, that's the key thing. I'm just going to slow down here in case I lost a lot of you and you want me to repeat anything. So again, here's the identity. The initial gradient with respect to phi of this function f under the distribution q with respect to the distribution phi can be rewritten as an expectation under a simple distribution, a base distribution times a gradient of this reparameterized function. Okay, some questions. That couldn't have been easy. Yes? Okay, so I'm going to leave that for a little bit, and then the question was how are we going to apply this result. So I'll come back to that in a little bit. But let's just take some questions around sort of what's actually going on, if it made sense, is it still intuitive what's going on, is the sequence of steps still clear? Any other questions on that? Okay, we're going to redo another derivation of this form, so come back again and ask me to explain it again afterwards. So again, many different names around how we use this change of variables and where this gradient is applying. The unconscious statistician was a simple, naive way. We call this idea stochastic backpropagation in a paper a while ago. Perturbation analysis, there's a whole area which is called perturbation analysis, which is around computing this gradient because it was applied in finance settings. In machine learning these days, you'll hear a lot of this phrase of the reparameterization trick, so that's where this comes from. And then you have this affine independent inference, which is sometimes another name. You'll see this in one or two papers. And you will use this, so what are the conditions when this needs to be used? Because I'm doing this reparameterization of f as a function of g, I can only use it when f is itself differentiable, when this gradient here is going to work. I need to be able to know this reparameterization or decomposition of q into a different set of variables. So q, I need to know its form as a base distribution and another transformation. So the simplest one that you have here is the Gaussian. You have sample from the 0, 1 Gaussian, and then you use a linear function, and then you can get any other full covariance matrix Gaussian. So you can use the inverse CDF. These location scale transforms, mu plus sigma times epsilon is 1, and there are other kinds of coordinate transforms that are multiplicative or exponential. And you need to make sure that this new distribution p of epsilon is actually easy to sample from. Because if p of epsilon is not easy to sample from, then you can't make an estimator of this quantity. You can't sample epsilon and then evaluate this quantity, because that itself is then an intractable problem. So maybe I'll just say a little bit about where this object gets used. So maybe the one I will use is reinforcement learning, and you'll see a bit about that later on in the week. In reinforcement learning, the single question of reinforcement learning is to maximize a reward function over a set of behaviors. So in reinforcement learning, the reward function is what we're calling this f. Every time you take an action, you get a reward, and you can evaluate this reward. Z here is the action itself, and what I'm calling q is this distribution over all the ways you can sample a behavior or take an action. So typically, if you want to learn how to take actions, the Q will be called a policy. If you want to learn a policy, you will need to compute gradients with respect to parameters of that policy, which are the phi's here. And you won't be able to do this easily, so then you're going to apply this trick to then compute the gradient and learn the behavior policy. So then you can do what we did in Atari. You can you can play the game, take random actions, use those random actions to update the policy, then use that new policy to take new actions, and then learn to play the game to superhuman level. Right, so that's sort of one example. And I'll give you another example if you were doing finance, for example. In finance, many of you may have heard of the Black-Scholes equation. This is the simplest equation. In finance, this Q distribution there will be a log normal distribution, and F will be a payoff function or a return function, which is how much money you get from an investment. What they want to compute is what is the grade. They're actually interested in the gradient itself, the gradient with respect to one input of that payoff function. And then that value means something about the risk of an investment, and based on that value, you will make an investment and you calibrate the investment accordingly. So there are several kinds of applications, very direct applications of this setting. And I have some references at the end where you can read more. Any other thoughts or questions on that past trick, reparameterizations? I don't know how much time I have left. If you just let me know. Okay, so I'll just quickly show you this one, and then we'll end. We don't need to go through it. The trick was basically that if you have a gradient of a log, you can use that. Just use the fact that derivatives of logs is gradient of the object inside divided by the thing on top. So the point is that you can jump from gradients of a log probability to gradients of a probability. And this is a useful thing because gradients of a probability will appear in many places. We could have derived this one together, but I'll leave that for you to show, which is a very useful property, that expectations of the gradient of a log is 0, and this quantity, the gradient of a log, is called the score. And if you apply this estimator, you will be able to derive a different way of computing the gradient we just did. And that gradient will be called the likelihood ratio method, or the reinforced method, or sometimes this automated black box gradient methods. And you can use this gradient instead when we have non-differentiable functions or non-analytical functions, but Q will still be easy to sample from, but Q now needs to be differentiable. So there'll be different trade-offs between these two kinds of gradients. There was one more trick on computing bounds of probability distributions, and many different ways of computing bounds and probability distributions that I wanted to talk with you a little bit, but Dave will sort of rederive this one for you, which is about how you use Jensen's inequality to compute bounds and the evidence of a probability distribution. And I mentioned right in the beginning that there was this idea of computing ratios when we looked at importance sampling. And I wanted to show you this trick on how we can compute density ratios very easily that's used in adversarial networks, noise contrastive estimation, and two-sample testing, which just involves sampling from the two distributions and learning a classifier. And if you go through the slides, you'll be able to follow the derivation to prove that if you want to compute the ratio of two probability distributions, all you need to do is just sample from them and build a classifier to discriminate between the two. And so the main point is that computing a density ratio is equivalent to the problem of computing class probability estimate. So these are my final words here, if you give me just 2 more minutes, that please always seek to strengthen your probabilistic dexterity. And in the end, it seems something simple. You can write all those tricks that in 45 minutes we could not cover, but these tricks become so fundamental that with them we can then expand and apply to many, many other areas of machine learning. So we looked at model inference algorithm paradigm, different kinds of models in the very beginning. Later on, you'll discover a few more applications, building products, in applications of science, in the core questions of intelligence, of how we can use all these probability tools to address them. And there are many other methods that you're about to learn about on variational inference and others. I did want to just make a quick question, the comment that was mentioned in the beginning. I've been asking many of you 2 questions over the course of lunch, and the ones that I have met earlier. One was, what is the thing you want to get out of these 2 weeks that you are here? And sort of what was the inspiration that they were looking for. And many of you are asking questions around looking for inspiration, getting a broad understanding of what machine learning is like, being able to answer that first question that I asked you, what is machine learning? But I think the thing that I hope that all of you will take of these 2 weeks is just the community of friends that you have built here today. The Machine Learning Summer School is sort of a rite of passage for people who come through machine learning. It is in this space that you will meet all your best friends for the rest of your career. There will be the people you will write a grant with, who you will apply to new projects with. There will be the people who will come to your weddings, the joke I made. There will be the people who will be at your divorce party. There will be the people who will, be with you for a very long time. I think it's a very special time that you are currently here. So please enjoy that time. The role of us building community and this problems of building stronger communities is sort of only the thing that can happen now. So please enjoy that thing. I've been doing a lot of work myself in this space around thinking of the strength of our own continent of South Africa and all our neighboring countries abroad in a project that we call the Deep Learning Indaba, which is around strengthening machine learning in Africa. We have done an amazing amount of work. I hope some of you will see in Nairobi, or if there are other people who want to learn a little bit more about machine learning and about this work of building community, please ask them to come and visit us in Nairobi. And again, please enjoy the rest 2 weeks. It has been a privilege to speak to you all, and I hope soon the tables will be reversed and I will be listening to some of your work. Thanks very much.